In this video, we're going to introduce the determinant of a matrix. The determinant of a matrix is a number associated to a square matrix, and one of its main uses is that it's going to give us information about whether the matrix is invertible or not. We'll see later on that it's also related to geometry in terms of areas and volumes. Okay, so in terms of the notation, we're going to denote the determinant of a matrix A by writing determinant of A like this, and sometimes it's also written in this way where we surround the matrix with two vertical bars instead of parentheses or brackets. So similar to the absolute value symbol. Okay, so we want the determinant to calculate to a single number, and for small matrices it's not too difficult, right? So for a 1 by 1 matrix just has a single entry A, right? So the determinant of this 1 by 1 matrix is just the number for that entry, right, which is A. For a 2 by 2 matrix, so we've actually already seen the formula for the determinant. To calculate the determinant of a 2 by 2 matrix, where the entries are A, B, C, D, in this arrangement, you calculate it as A times D minus B times C. And notice that this formula AD minus BC appears in the formula for the inverse of a 2 by 2 matrix that we introduced previously. Okay, so the 2 by 2 determinant isn't too difficult to calculate, right? So here I have a 2 by 2 matrix, and again these two vertical bars means that I want to calculate the determinant, right? So these are the entries A, B, C, D, right? So this is A, this is B, this is C, and this is D, right? So this arrangement, and so the formula is AD minus BC, right? So writing it out for this matrix will be negative 3 times 6 minus 5 times negative 7. And then now we just calculate this, right? So this is negative 18, and then minus a negative becomes a plus, and then 5 times 7 is 35. So now we calculate negative 18 plus 35 gives us 17. So we've calculated the determinant of this 2 by 2 matrix as 17. Okay, so we know the determinant for a 1 by 1 matrix, the determinant for a 2 by 2 matrix. What about for larger matrices? So in this section, we're going to calculate determinants of larger matrices using a method called cofactor expansion. Basically, what's going to happen is we're going to write the determinant of a larger matrix in terms of smaller determinants, and we already know how to calculate smaller determinants. So essentially, it's a way of calculating determinants recursively. Okay, so before we discuss cofactor expansion, we need to go over what exactly is the cofactor of a matrix. Okay, so the definition is here, right? So for a square matrix, so first something called the minor. So each entry in a matrix has a corresponding number called the minor of that entry, and the minor of that entry is calculated as the determinant of the matrix obtained by deleting the ith row and the jth column of the original matrix. And the cofactor is obtained from the minor, as this formula here, so minus 1 to the I plus jth power times the minor, right? So the minor is calculated as a determinant, right? So it's just a single number, and the cofactor just has this -1 power in front of the minor. So basically the cofactor is either the plus value of the minor or the minus value of the minor, depending on whether I plus j is even or odd, right? So this extra factor is either a +1 or a -1, depending on if I plus j is even or odd. So it's best to understand how to calculate the minor visually by actually removing the row and the column of the matrix and looking at what the entries are left over. So let's look at how to calculate a couple of the minors for this matrix here. Alright, so here I have a 3x3 matrix, and I'm going to calculate two different minors. Alright, so this one is going to calculate the minor for the entry in row 2, column 1, so the entry here, and then here I'm going to try to calculate the minor for the entry in row 1, column 3, so this entry here. Okay, so first let's calculate M21, right? So again, M21 means that I want row 2, column 1. So first I cross out row 2 and also cross out column 1. So I put a circle in the -2 here because it's useful later on, but for now that's not actually part of the calculation, right? So so if I cross out row 2 and column 1, I have 4 entries that are left over, right? So 1 0 0 2, and this forms a 2x2 submatrix, and so the minor will be the determinant of this submatrix. Okay, so I want the determinant of the entries that are not crossed out, which again is arranged in exactly this way, right? So 1 0 0 2. Okay, so now we calculate the determinant. So we already know how to calculate the 2x2 determinant, right? So it's just AD minus BC. So AD is 1 times 2 minus BC is 0 times 0. And then this just calculates to 2. Okay, so M21 is equal to 2. And then now let's calculate the corresponding cofactor. Right, so the formula would, in this case, would be just -1 to the I plus j, right? So this is 2 plus 1. And then M21, right? So this -1 power times the minor, which we've calculated previously, right? So 2 plus 1 is odd, right? So that means this is a -1. And M21 again we calculate is 2. So -1 times 2 is equal to -2. So again, this is odd, so that's why we have this extra -1 here. Okay, so that's how we calculate the cofactor for this entry. Okay, so this next calculation is similar, right? So now we're working with row 1, column 3. So I cross out row 1 in column 3, and now we're calculating M13, right? So I get a 2x2 submatrix again, and I arrange the entries where they should be, so -2, 4, 1, and 0, and now I calculate the determinant using the AD minus BC formula. Right, so -2 times 0 minus 4 times 1. So this is a 0, and then this part is -4, so I get -4. So M13 is -4. And then now I calculate C13, which again, according to the formula, is -1 to the I plus j is 1 plus 1 plus 3. Then M13, which we've previously calculated as negative 4. Right, so now this is even. Right, so this is now, so the even makes it a plus 1. And then again, M13 is negative 4. So I get 1 times negative 4. So C13 is negative 4. So basically what this extra factor does is it takes the opposite sign if this sum is odd, and then it takes the same sign if this sum is even. Okay. So that's how you calculate the cofactors, right? We've only calculated for 2 of the entries of this matrix, but any matrix has a corresponding cofactor for every single entry, right? So for this matrix A, I could calculate 9 different cofactors. Okay, so continuing on, if you look back again at the formula for calculating the cofactor, right? So again, we have this minus 1 to the I plus j as part of the calculation. Right, so as we said before, minus 1 to the I plus j is either plus 1 or minus 1, depending on if I plus j is even or odd. Right, so if you look at how to calculate I plus j as you move across the entries, right, so the I plus j is going to alternate between even and odd. And so you can see that as you calculate the I plus j, for the corresponding entries, it's going to alternate between positive and negative. Right? And then you get these patterns for 3 by 3, 4 by 4, 5 by 5, and so on. Right, so for 3 by 3 matrix, right, so 1 plus 1 is even, so you get plus, and then 1 plus 2 is odd, so you get minus. 1 plus 3 is even, so you get plus. 2 plus 1 is odd, so you get minus, and then so on, right? So again, it just alternates plus, minus, plus, minus, plus, minus, plus, minus, plus. And then the pattern continues for larger matrices, right? So again, you just keep alternating pluses and minuses. And so you can just keep this in mind as we continue on to do the cofactor expansion, right? So there's an extra plus 1 or minus 1 coming from this thing corresponding to each of these entries in this pattern. Okay, so now let's finally go over what it means to do cofactor expansion. So in the definition of cofactor expansion here, so we have a square matrix, and the description here is to expand along the first row of the matrix A. Right, so you can see that the first index here for A is fixed to be 1. Right, so that's why everything is occurring in the first row. So basically, what this determinant formula is saying is that you calculate the determinant by taking each of the individual entries along the first row, and then for each entry you multiply by the corresponding cofactor. Right, so this is the first entry in row 1 times the corresponding cofactor, second entry in row 1 times the corresponding cofactor, and then so on until the last entry in row 1 times the corresponding cofactor. So that's basically what this formula is saying, and then this is just using sigma notation to shorten this summation. Okay, so the description here is talking about the expanding the entries of the first row, but in actuality, the formula for the determinant can be expanded along any row or any column. Right, so you can expand on any row or any column, and sometimes it's actually advantageous to use a different row or a different column than the first row. But for now, let's just stick to the first row because it's the most convenient. Okay, so so here we're going to discuss exactly how this expansion by cofactor works for this example 3x3 matrix. Okay, so I have 3 entries in the first row, right? So 3, 1, and 0. And so each entry in the matrix is going to contribute one of the terms in the determinant expansion. And then I also need to calculate the cofactors for each of these 3 entries, right? So I need each of those cofactors also. So let's first visualize the cofactors. So to save time, I'm just going to copy and paste this thing. Oh, that didn't work out. Let's try that again. Okay, so okay, so again, I need 3 cofactors. So I need to visualize 3 of them. Let's move this up a little bit to give me some space. Okay, so now let's identify how to obtain the cofactors, right? So the first entry in the first row is this entry, and I need to delete the first row and first column. And then now the second entry in the first row, delete first row, second column. And then now the third entry in the first row, delete the first row and third column. And then now we can see the 2x2 submatrices in each of the cases. Okay, so now let's set up the determinant. Okay, so how should I write the determinant, right? So first, I take into account the sign pattern, right? So the first row is plus, minus, plus. Right, so that's the minus 1 to the I plus j part, right? So this first entry is a plus. And then I need the entry in that position. So the entry is 3. And then times the determinant of the submatrix. Right, so this is the minor, right? Not the actual cofactor. The cofactor is the minor together with this extra sign. Okay, so here is the determinant of the submatrix. So 4, -1, 0, 2. And then second entry had the minus in the pattern, right? So the entry is 1, and the determinant of the submatrix, so -2, 1, -1, 2, and then plus, right, because plus, minus, plus, and then the entry is 0. Determinant of the submatrix is -2, 4, 1, 0. Okay, so this is what the cofactor expansion for the first row looks like for this determinant. And then now you can see that we've reduced the calculation of the determinant to a bunch of 2x2 determinants, and we know how to calculate 2x2 determinants. The AD minus BC formula. right? So let's just now calculate that, right? So this is 3 times 4 times 2 minus -1 times 0, then minus 1, -2 times 2 minus -1 times 1, and then plus, technically I don't have to calculate this, right, because it's just 0 times this determinant, and I know that this is going to cancel out, but in any case, let me write it out in any case. So 0 times, I know this thing is going to be 0, minus 4 times 1. Right, so this whole thing is 0. And then now let's calculate this. This is 8 minus 0, so that's just 8. And minus 1 times, what is this? -4 minus a -1. So -4 plus 1 is -3. So I get 24, and then minus becomes what? 24 plus 3 is equal to 27. Okay, so we calculated that the determinant of this matrix is 27. So this is the cofactor expansion. Okay, so before we continue, let's go back and again remind ourselves the different parts that go into setting up the determinant, right? So we have the sign pattern. For row 1, so the row 1 sign pattern, and then what else do we have? You have each of the entries row 1, right, which I've highlighted in green here, and then finally each of these are the individual minors, right, because the sign pattern and the minor together gives us the cofactor. Okay, so that's how we set up the cofactor expansion. Okay, so here we have the same matrix as before. Right, so you can go back to the previous page. All right, so you can see that it's exactly the same matrix. We're going to calculate the determinant again, except now we're going to look at how to expand along the second row, and then we'll see that the determinant is still the same, right? So it doesn't matter which row or column you use. Okay, so to save time, I've already visualized how to obtain the submatrices for each of the entries in the second row, right? So here, crossing out first column, second row. Here, crossing out second column, second row. And here, crossing out third column, second row. Okay, so after visualizing this, now we can just set up the cofactor expansion, right? So if you remember the second row of 3 by 3 matrix, the sign pattern, the sign, let me write it here, sign pattern for row 2 of a 3 by 3 goes minus, plus, minus. Right, so I have a -1 for the first entry, then the actual entry is a -2, And then now I take the determinant of the submatrix, so 1, 0, 0, 2. And then the second entry has a plus, and then the actual entry is a 4. And then determinant of the submatrix, 3, 0, 1, 2. And then third entry has a minus, so an extra minus, and then the entry itself has a -1. And then the submatrix is 3, 1, 1, 0. Okay, so that's the expansion, and then now we just need to calculate. Okay, so minus 2 becomes a +2. And then, okay, so let's just calculate these determinants. So this is 1 times 2 minus 0, so that's 2. And then plus 4. This determinant is 3 times 2 is 6 minus 0. And then this minus becomes a +1 times 3 times 0 is 0 minus 1. There's a -1 here. And then now we just calculate what is this. This is 4. This is 24. This is -1. And then 4 plus 24 minus 1 gives me 27. Okay, so again, we see that it's the same as before. And so again, we did row 1 and row 2, but if you do it yourself, you can see that whether you do row 3 or column 1 or column 2 or column 3, it's all going to be still give you the same number for the determinant. Okay, so so on the bottom of this page, we discussed the determinant of a triangular matrix, whether it's upper triangular or lower triangular. And we'll see that the formula for calculating the determinant in this case is actually very straightforward, right? So for an upper triangular or a lower triangular matrix, to calculate the determinant, you just multiply all the diagonal entries together. So all the entries on the main diagonal, and then none of the other entries contributes to the determinant. So here we look at a 3x3 example, but again, it's true for any upper triangular or lower triangular matrix. Right, so we can see that this is upper triangular, right, because all the entries below the main diagonal are 0. So I have an upper triangular matrix, and according to this this theorem, is just to calculate the determinant is just multiplying the 3 diagonal entries together, right? So in this case, A times B times C. But let's look at cofactor expansion along the first column to see where this A times B times C really comes from. So cofactor right, so first column, it's plus minus plus pattern, right? So plus minus plus. So let's write it out, right? So first entry is A, right? So it's plus A times the submatrix, right? So if I cross out the first row and first column, these 4 entries are left over. Right, so it's B, Z, 0, C, and then minus, then we have a 0 here, and the submatrix there crossing this out, so that's these 4 entries. So x, y, 0, c, then plus this entry, which is a 0, and then the submatrix cross this and this, so these 4 are left over. That's x, y, b, z. Right, so again, this is 0, so this goes away. This is 0, so this whole thing goes away. Right, so now you're just left with a times this determinant, but there's a 0 here, right? So this is just b times c. Okay, so I mean, here we did an upper triangular, and it's only a 3 by 3. But for larger matrices or lower triangular matrices, it's similar, right? Because you can just choose the row or column that has the single entry, and then all the others are 0, and then the expansion will look exactly like this. Okay, so triangular matrices, calculating determinant is pretty easy. So one more thing to keep in mind is when choosing the row or column to expand with, typically you can save a lot of time if you choose the row or column with the most zeros, right? Because as you can see, when you have 0 entries, they cancel out, those terms cancel out when you do the expansion. Okay, so on this last page, we'll look at calculating the determinant of a 4 by 4 matrix. But we're going to see that once you understand the process of cofactor expansion for a 3 by 3 matrix, any larger matrix will be similar. Okay, so if you look at this matrix, right, so the first column has 2 zeros in it, so probably expanding by the first column will be easiest, right? And if you remember, the first column for a 4 by 4 matrix is plus minus plus minus. So the sign pattern. Right, so again, to save time, I've already crossed out the row and column for these 2 entries, right? So we can see the submatrix here. So now let's write out the expansion. Right, so determinant of A, right? So first entry has a plus, and the entry itself is a 5. Now I want the determinant of the submatrix, which is 6, 4, 12, 2, negative 3, 4, 1, negative 2, 2. And then second entry is a minus, and the entry itself is a 4. And the submatrix, 3, 0, 6, 2, negative 3, 4, 1, negative 2, 2. So you can see here now in the process of writing out the cofactor expansion, the calculating the determinant of the minor now involves 3 by 3 matrices, right? So this is essentially how determinant works, right? So when you do the expansion, it reduces to a bunch of determinants that are one size smaller, and so basically, to calculate a 4 by 4 determinant, you need to know how to calculate 3 by 3 determinants, right? And so so here we'll calculate each 3 by 3 determinant separately, right? So the first one, 6, 4, 12, 2, negative 3, 4, 1, negative 2, 2. So here I'm just going to do the first row. because I mean there are no zeros, right? So it doesn't really matter, right? So if you remember, it's plus minus plus, right? So I'm just gonna write out real quick. So 6, and then the submatrix is -3, 4, -2, 2, and -4, and 2, 2, 4, 1, 2, and plus 12, 2, -3, 1, -2. And then now we just have to calculate this, right? So 6, and then what is this? This is -6 minus a -8. So -6 plus 8 is 2, and -4. What is this? This is 4 minus 4, which is 0. And plus 12, what is this? 2 by 2. It's -4 minus a -3, so -4 plus 3, which is -1. So this is 0, so it's 12. 12 minus 12 is equal to 0. Okay, so this determinant is 0. Alright, so now we still have this 3 by 3 determinant. So what is this? This is 3, 0, 6, 2, -3, 4, 1, -2, 2. Right, so again, I'll do the first row that has a 0. It's plus minus plus. Alright, so what do we have? It's 3 times these 4 entries, so -3, 4, -2, 2, and -0. It doesn't really matter what's here, but it's 2, 4, 1, 2, and then plus 6. The entries are these 4. 2, -3, 1, -2. This is 0. So what is this? This is 3 times -6 minus a -8 is -6 plus 8 is 2, and plus 6 times -4 minus a -3 is -4 plus 3 is -1. So this is 6 minus 6, which is again 0. Right, so the determinant of A is 5 times this was 0, then -4 times this whole thing, which was calculated as 0. And this is 0, this is 0, so the whole thing is 0. Okay. So we see that the whole determinant is equal to 0. So that's basically how calculating the determinant of larger matrices works, right? So determinant of 4 by 4 matrix will reduce to a bunch of 3 by 3 determinants, which in turn reduces to a bunch of 2 by 2 determinants, and so it's recursive in that way. But you can see that as the matrices get larger and larger and larger, it becomes very tedious to do the determinant calculation. So let's look at how to calculate determinant on a calculator. So let's look at how we use the graphing calculator. Okay, so here I've entered the matrix into my matrix H here, right? So this is the original matrix, right? So you can see that this is my matrix H, right? So now how do I calculate determinant, right? So you go back into the matrix menu, so second, and then matrix, and then under math, the very first thing is exactly the determinant, right? So you choose that, and then now we need to choose the matrix, right? So I want my matrix H. So H is number 8, right? So here I want to calculate the determinant of H, and then I enter, and then you can see it calculates it as 0, right? So basically, again, the determinant option is a second matrix. Go over to the math menu, and it'll be the first one here. The screenshot here that I took previously was using the matrix A, but you can see it's still the same matrix as before, because I did this calculation much earlier using a different matrix. But anyway, that's how we use the graphing calculator, and we get the same determinant as we've calculated by hand.